What specific problem does your method aim to solve in the context of understanding LLMs predictions?
The method presented in the paper aims to solve the problem of understanding the predictive power of token embeddings in large language models, LLMs, by quantifying their capability to predict the next token in a sequence. Specifically, it introduces the prediction residual (PR) metric, which measures the fraction of variance unexplained in the next token prediction task, thereby providing a clear assessment of how well the model's embeddings can predict subsequent tokens. By analyzing the PR across different layers of the model, the study reveals the law of equi-learning, which describes the consistent reduction in predictive power as one moves from the first to the last layer. This insight challenges the notion that LLMs operate chaotically and instead highlights a structured learning process that can inform model training and optimization. Ultimately, the method enhances our understanding of LLMs' internal mechanisms and their performance across various architectures and pre-training tasks.
How does the proposed method work? Illustrate the algorithm step by step, especially how you compute the prediction residual (PR) across layers.
The proposed method evaluates the predictive power of a pre-trained LLM by calculating the prediction residual (PR) for next token prediction across its layers. First, the model processes a sequence of tokens, generating embeddings at each layer, with the last embedding from the last layer used to predict the next token. A dataset, D, is formed consisting of pairs, h_t text last caret s, x_s_t plus 1, where h_t text last caret s is the last embedding and x_s_t plus 1 is the next token to predict. The PR is computed using a linear regression model where the prediction x_text next equals w_c_dot h plus b is fitted to the dataset D, and the PR is quantified as the fraction of variance unexplained, defined as 1r², where r² is the coefficient of determination. This process is repeated for each layer, L, of the LLM, allowing the calculation of PR values, PR_L, to observe how predictive power evolves, typically showing a decay pattern characterized by the law of equi-learning.
Can you provide a simple example that illustrates how the prediction residual, PR, is calculated for a given sequence of tokens?
To calculate the prediction residual PR for a given sequence of tokens, consider a sequence S with tokens x_s_1, x_s_2, l.s x_s_t. The LLM generates an embedding, h_t text last caret s, from these tokens, which is then used to predict the next token, x_s_t plus 1. The prediction is modeled as x_text next equals w_c_dot h_t text last caret s plus b, where w and b are parameters determined through least squares fitting on the dataset, D. The PR is calculated as the fraction of variance unexplained, defined mathematically as PR equals 1r², where r² is the coefficient of determination from the linear regression. A high PR value indicates that the model's predictions are not closely aligned with the actual next tokens, while a low PR value suggests strong predictive capability of the token embeddings.
What are the theoretical or practical benefits of using your method for evaluating LLMs compared to existing approaches?
The method introduced in this paper, specifically the law of equi-learning, offers several theoretical and practical benefits for evaluating LLMs compared to existing approaches. Firstly, it provides a precise geometric characterization of how contextualized token embeddings evolve across layers, allowing for a nuanced understanding of the learning dynamics within LLMs. This contrasts with traditional methods that may overlook the contributions of intermediate layers, as the equi-learning law ensures that each layer contributes equally to the model's predictive power. Additionally, the law's universality across various architectures and pre-training tasks enhances its applicability, offering insights into model scaling and the impact of pre-training data quality. Practically, this method can inform the optimization of training processes, such as adjusting learning rates across layers and preserving the equi-learning law during model pruning and fine-tuning, ultimately leading to more efficient LLMs. Lastly, the law facilitates improved evaluation of LLM capabilities by emphasizing the importance of high-quality probing data, which can enhance interpretability and the assessment of model performance across different tasks.
How was the method validated or tested in your study? What datasets and metrics were used to demonstrate its effectiveness?
The method was validated by assessing the predictive power of the LLMs through the prediction residual (PR) metric, which quantifies the model's capability to predict the next token based on contextualized token embeddings. The dataset used for this evaluation was constructed from sequences of tokens denoted as D equals H underscore T text last caret S, X caret S underscore T plus 1 mid 1, lec S1, lec T underscore S1, where H underscore T text last caret S represents the last embedding from the LLM. Various probing datasets were employed, including book corpus, C4, Open Web Text, Wikipedia, The Pile, Red Pajama, and Oscar, to calculate PR and evaluate the law of equi-learning. The effectiveness of the method was demonstrated through the consistent emergence of the equi-learning law across different architectures and the correlation of PR values with layer indices, indicating a systematic reduction in predictive power across layers. Additionally, the study explored the impact of training steps, epochs, and data repetition on the emergence of the law, further validating the robustness of the method.
What limitations or drawbacks did you encounter while applying your method, particularly regarding model scaling or the choice of pre-training tasks?
While applying the method, we encountered limitations related to model scaling and the choice of pre-training tasks. Specifically, larger models exhibited a reduced predictive power, PR, for both first-layer and last-layer token embeddings, suggesting that while they may enhance feature learning capabilities, their individual layer performance could be less effective compared to smaller models. Additionally, the emergence of the law of equi-learning was inconsistent across different pre-training tasks. For instance, while it appeared under masked language modeling, MLM, for Bert and Roberta, it was noisy due to the complexity of token replacement strategies. In contrast, the span corruption SC task for T5 did not yield the law's emergence, likely due to its encoder-decoder architecture complicating the learning of contextualized token embeddings. These findings highlight the critical role of pre-training task selection in facilitating the law's emergence, and suggest that more naturalistic tasks may be necessary for optimal performance.